好，邀请一下。So it's also a pleasure for me to introduce Andrew speaker. He's a postdoctoral researcher in the Department of Philosophy at Bochum, and his research focuses on non-logical logics and their applications to issues on philosophical interests. So again, let's have 40 minutes around 40 minutes for presentation, and then 50 minutes for Q&A.
Thank you. Thanks to Luis and everyone else for organizing. It's a pleasure to come back to Mexico, especially after the pandemic in between. So it's lovely to come and visit once again. And I'll be talking about some recent-ish work on what I'm going to call Kapsner complementation. And I hope Andy Kapsner is still online. In which case, hello. And yeah, so as you can see from the subtitle, this is an attempt to sort of start to think about a general algebraic semantic framework for talking about some logics, which, even if they're not strictly speaking connexive, they're sort of fellow travelers of the next logics. We're called Kapsner strong logics by Luis and Ellie in a nice paper of theirs. So I'm going to start by talking about Kapsner's notion of strong connexivity. And I will build from there to Kapsner strength or Kapsner strong logics, speaking about how the motivations for strong connexivity give rise to motivations for Kapsner strong logics, and how Kapsner strong logics are sort of nice from a technical perspective, which is why they seem to ask for a certain algebraic standard treatment. After having motivated things, I'll give definitions for the two key concepts, K and SK complementation, which will be properties of unary operators on partially ordered sets, which I'll use to interpret negation, which will have the properties that are definitive of Kapsner and strong logics. I'll give the definition of these two complement operators. I'll state some sort of basic facts about them. And then the bulk of the talk will be taken up by giving examples of cosets, coalgebras that have complement operators of these two kinds. I'll talk a little bit about how this algebraic framework is a generalization of one studied by McCall in the 70s. I'll give a couple of constructions starting from Boolean algebras and then starting from general cosets to obtain cosets that have these kind of operators. And then I'll close with some discussion for future work, which hopefully you will find motivating. So you will join me in thinking about these interesting things. Right. So Kapsner, in a paper in 2012, which interestingly, I think, is in the first issue of the journal Thought, proposed that in addition to the standard requirements for connexivity, which, as we discussed in the last talk, were proposed by McCall in the 60s, we have, in addition to these properties concerning validity and invalidity, like Aristotle's theses, Boethius's theses, and the asymmetry property, Kapsner suggested we might also demand some further, stronger conditions that call for unsatisfiability. For instance, that unsat 1 tells you that neither of these formulas, which are the negends of Aristotle's theses, are satisfiable. And furthermore, that the set containing both A arrow B and A arrow not B is also unsatisfiable. So on this way of understanding these things, not only must these formulas have countermodels, but in fact, they must not have any models. So we require this very strong separation, as it were, between a formula and its negation. And Kapsner suggested that this, for reasons I'll discuss very briefly in a moment, that these constraints are somehow expressive of certain core commitments of at least contemporary connexivists. So one way you might motivate connexive logic, I'm not going to be talking at all about history in this talk, so this is just off the top of my head ways of motivating connexive logic, or ways that reflect some ways that have been talked about. Although after hearing Sarah's talk, I suspect there are definitely historical precedents here. You might give a motivation that relies on a similar story that has been told for relevant and analytic containment logics, where we're calling for some kind of meaning connection between antecedent and consequent. And in particular, if we take the validity of an implication formula as an expression or maybe a representation of entailment, once again, sort of blurring the line between consequence and conditional, then we'll say that whenever A entails B, that must mean there's some meaning containment that obtains between A and B. Now, if we take that sort of meaning connection or meaning containment kind of story, then the wide scope negations in Aristotle and Boethius' theses, namely these ones and these ones, they express something like entailment failure, failure of implication. And then what's distinctive about the connexivist story is that whatever the meaning containment or meaning connection relation is that we're going to require between antecedents and consequence and entailment claims, this relation shouldn't obtain between any formula and its negation. And if it entails between a formula and another formula, it doesn't obtain between that first formula and the negation of the second. And basically, the kind of story that Kapsner tells about strong connexivity is that something like this expresses a core commitment on the part of the connexivist, and that these unsat conditions help strongly connexive logic better express those core commitments. So as I mentioned, Luis and Elliott in a nice paper in 2016 give a wide-ranging catalog of connexive systems and propose to call logics that satisfy the unsatisfiability conditions Kapsner strong, because a logic may satisfy those without satisfying the usual connexivity criteria. And indeed, there are reasons, I think, to be interested in Kapsner-Strong logics, maybe not as against, but in addition to strongly connexive logics. For instance, the unsat clauses, unlike Aristotle and Boethius, are first degree. So the main connective is the conditional, and there are no conditionals occurring in the scope of that main connective. And so we can study these systems in a reasonably nice first degree sort of way. And looked at that way, the Kapsner strength criteria, these unsat conditions, needn't concern implication directly, but rather the relation of entailment that it's meant to express, if we express that in a different sort of way. And second, the unsat clauses are interesting in being unsatisfiability clauses, which, at least as far as giving requirements on logics, are rather different and rather interesting from the usual kinds of clauses we use to motivate a logic, which usually concern validity or failure of validity or something like that. So I think these are some properties of, in particular, Kapsner-Strong logics that make them kind of nice and amenable to a particular kind of investigation, which is what I'm going to talk about now. Right, so let me reframe the Kapsner strength conditions in a properly first degree way. And to do that, I'm going to consider logics in, if you're thinking in done in Hardegree's book, binary assertional logics, or if you're thinking in Humberstone terms, is a formula-formula logic, where we take a logic to be a set of formula-formula sequence, like that. And I will write something like this to state that this formula-formula sequence is valid in place of saying that the pair belongs to the logic. Now, if we do that, and we're concerned with logics which are complete with respect to some class of models, given that we have some notion of satisfaction with respect to that class of models, then the unsat conditions just say that no model satisfies either of these formula-formula sequence, and no model satisfies both of these. And that way, when framed in these terms, Kapsner strength doesn't actually concern implication, mainly it concerns negation. It's about the relationship between a formula and its negation, and between pairs of formulas and the negations thereof. And furthermore, there's a very close relationship between formula-formula logics on the one hand, and partially ordered algebras on the other hand. And if we think about semantics in terms of partially ordered algebras, and those giving us our classes of models, there's a very simple and quite natural way of semantically expressing these properties. So, to state that, to sort of give these definitions, the kind of modeling machinery I have in mind is the following. Suppose we've got a partially ordered algebra graphed with some operations, and a model that assigns to every atomic formula some element of the Poe algebra, extended to a homomorphism over the language. Then a very natural way to express satisfaction of a formula-formula sequence is just in terms of the order. A sequence A, sequence B is going to be satisfied just in case the value of A is below that of B. And looked at through that lens, the unsat conditions express properties concerning the relation between the operation that interprets negation and the underlying order. So I'm going to give definitions of these key notions and then start to fill in the story. So in setting out the target classes of algebras, I'll pull apart these two unsat clauses concerning sequence systems, because as we'll see, the latter is a much more stringent condition and really constrains what kinds of models we can build. Okay, first definition of a Kapsner complemented or K-complemented coalgebra. Let this be a partially ordered algebra with a unary operation. I'll say that that unary operation is a K complement, just in case for any A is not below its negation and its negation is not below A. So that is to say A and not A are incomparable. In that case, I'll call big A K complemented coalgebra. There are some properties that fall out immediately that are going to be pretty obviously or pretty immediately familiar if you're thinking about connexive logics in sort of the axiomatic or matricial sort of method. First off, any such K-complemented coalgebra is neither going to be upper nor lower bounded, because an upper and lower bounds, neither of them are incomparable with anything. Furthermore, there's also not going to be any explosion. In particular, not only will there be no explosion with respect to this negation and, say, a conjunction, there won't be anything you can write down using just the operations in the algebra that's below everything, because nothing is below everything because there's no bottom. So these are strongly paraconsistent. Not only do you not get explosion in this sort of usual way, you don't have anything like explosion available. There are too many propositions for that. So that's one immediate consequence. Another is that if this thing is a semi-lattice, so if we have a lattice meet or a lattice join operator representing the usual conjunction and disjunction, then this negation will not be order inverting with respect to that order. So A being below B will not tell you that not B is below not A. And I'll say why that is in a moment, although it's basically from a familiar fact that's been discussed a couple of times already today. And if A is a lattice, if it has both a meet and a join, then it won't satisfy either of these De Morgan laws. Basically for the reason that if it satisfies either of these, then we get order invertingness back immediately. Right, so for 2, the fact that this can't be order inverting is that if we had a meet around, we'd get that contradictions are below their negations. And if we had a join, we'd have that any instance of the longitude middle is above its negation. So we would just lose the K complementedness immediately. And as I said, either of these De Morgan laws are sufficient to ensure that this thing will be order inverting with respect to the lattice order. For reasons that have, for instance, been discussed in the context of gaggle theory for negations. If you're interested in that, basically both of these tell you enough of the distribution type of these operators that we get, or this operator, I should say, that we get order inversion just immediately. Okay, so that's a K-complemented coalgebra. That's some simple facts. The next step, I should say, this is to capture the unsat 1 clause that no formula is implied by its negation or implies its negation. If we go a step further and require the unsat 2 clause, we get a definition of an algebra of the same kind of type, but require that for any pair of elements, either A and B, either A is not below B or it's not below not B. So any model will satisfy at most one of these two equations. Now, this is a much more stringent property because first, S complementation entails SK complementation entails K complementation. And furthermore, we know that if you've got an SK complement, this thing cannot be a meet semi-lattice. Why? Point 1 just follows from the fact that A is below A and not A is below not A. So by this clause, then we get the K complementation clause that A will not be below not A and not A will not be below A. And for point 2, note that if we had conjunction around, we'd get both of these inequations immediately. So as I mentioned, SK complementation is significantly stricter than K complementation, which is why I'll pull them apart. Because as it turns out, we can define some interesting lattices using that are K complemented, but we can't have any lattices that are SK. Right. So those are the core definitions. Let me briefly reflect on where these definitions come from when we look at this structure, when we look at these logics algebraically, and make a point that an algebraic version of a point that's been made a couple of times already today, which is one way to understand these properties is to compare the behavior of negation in the kind of partially ordered algebras I've been discussing with the behavior of the usual Boolean complement operator in Boolean algebras of that type. Note, if A is not the bottom element, then A is not below its negation. And furthermore, if A is not the top element, then it's not above its negation, right? And also, if A is not the bottom, then it can't be below any pair of both an element and its negation. So, in a variation on a familiar story in connexive logic circles like this one, rectangles, a non-humble connexive style negation generalizes the behavior of classical negation such that behaviors you get for classical negation on logically contingent propositions are required to hold for every proposition. So if we were to take a version of K and SK complements, the criteria for K and SK complementation, and just fix them for non-extremal elements of, say, Boolean algebras, we would just get properties that Boolean negation already satisfies. So insofar as there's something sort of formally interesting to study in the area, it's by not going humble, but going stronger and looking at what the result is. So, as I said at the beginning, and after a bunch of warming up, the aim of this talk is to investigate some of the properties of SK and K complemented coalgebras and the logics of which these structures are models. So, as I mentioned, I'll be talking about models of formula-formula logics where the order is used to interpret the sequence separator. And as usual, I'll say that a sequence is satisfied on an algebra that's satisfied by every model. I'll say it's valid with respect to a class of algebras in case it's satisfied by every algebra in the class. And I'll say that a set of sequence, formula-formula sequence, is the logic of a class of partially ordered algebras just in case it validates exactly the sequence validated by the class. Now, if we do that, the basic axioms and rules that we're going to get for logics of classes of coalgebras are things like reflexivity and transitivity with respect to the sequence separator. And furthermore, I didn't write it on the slide, but I'll just say it, a form of congruentiality with respect to all the other operators, so that if a bunch of formulas, if for a bunch of formulas, however many are involved in the arity of the operator in consideration, are provably equivalent in the sense that both A sequence separator B and B sequence separator A are provable, then we'll be able to prove any sequence between a formula in which A occurs and a formula in which B occurs substituted in for A. But these are sort of the basic properties we get for logics. And if we've got if we're talking about, say, distributive lattices or semi-lattices or other kinds of things, we'll add familiar looking axioms and rules for the lattice meet, the lattice join. For instance, that A meet B is below A, so A conjunction B entails A, and so on and so forth. So that's sort of the basic shell of what these formula logics are going to look like, given that we're talking about partially ordered algebras in the first place. But behavior of negation is sort of interestingly different than usual because the constraints we've put on these are negative constraints. So all we're doing is ruling out certain models. We're not ruling anything in. So basically all we can say about negation in virtue of the definitions I've given is a version of this congruentiality rule that I sort of talked through a moment ago with respect to negation. Because beyond this, we can build all sorts of partially ordered algebras with negations that satisfy the negative criteria for K and SK complementation, which also countermodel all sorts of other properties you might want your negation to behave. As I say here, because we haven't actually specified any behavior negation ought to exhibit, just some behaviors it oughtn't to exhibit. And so, in general, the flavor of question that seems most interesting in the area concerns what properties are compatible with negation being a K or SK complement. I already told you about two De Morgan laws that are not compatible, but I'll give some constructions of algebras that show that all four of these are okay. So the other two De Morgan laws are fine. We can take negation to be a period 2, no problem. And the questions that then come up are what other behaviors of negation are allowed? What is not ruled out by these strong negative constraints given by K and SK complement? Right, let me give some definitions in order to set up the results I'm going to prove or at least talk through. Suppose that A and B are SK or A complemented coalgebras of the same type. I'll say that B extends A just in case there's a surjective order-preserving homomorphism from A to B. That is a function from A to B that satisfies these three properties here. So that's to preserve the order, we need to preserve structure, and we need to be surjective so that everything in the target is in the image of something in the signal, the source. Thank you. I'll say furthermore that B properly extends A just in case no such H is order reversal. So we don't, in fact, have an embedding between A and B. So proper extension is an extension where we actually have collapsed some distinct elements from the source in the target. You can also think of it as requiring that this thing shouldn't be an isomorphism. Furthermore, given a class of partially ordered algebras with an element A, I'll say then that A is maximal in the class in case for any B that properly extends A falls outside of the class. So what we're looking at here then are properties that extensions of a partially ordered algebra can satisfy while still falling in the class in question. Some classes I'll be talking about are things like this K complemented distributed lattices or SK complemented joined semi-lattices. So, and the question then are what simplifications can we perform in the algebra in question while still being K complemented and still being distributive, or still being SK complemented and still being a joined semi-lattice. Right, and I think this is a pretty good formal analog of the question of what properties are compatible with respect to negation being an SK complement. Because we can specify algebras that we can't simplify any further, and then look at the class of maximal algebras with respect to certain classes to figure out what are like the most properties we can build in while not contravening the things we don't want to contravene. So what I'm going to do is give a bunch of examples of how you build coalgebras of these kinds, including some maximality results that certain algebras are the simplest we can do in some sense, and talk about some of their properties. Right, so one natural place to start is with George McCall in 1975 in a section of Entailment Volume 1, published by Anderson and Belknap. McCall gave already a version of algebraic semantics for connexive logics, which generalized his semantics for CC1, which we've already seen in the previous talk, where he started from Boolean algebras and then performed some surgery and got some things which I'll show you are SK complement. So here's the surgery. I'll say that a McCall algebra is something of this type, although I should have dropped those two. Please ignore those things. Where we start off with a Boolean algebra and a proper prime filter on the Boolean algebra. So it's got to be non-empty. I also should write here that it's got to not be the whole set, and it's got to be a filter, and it's got to be prime. So it respects the usual truth conditions for conjunction and disjunction. Now we take D, our proper prime filter, and define U to be its complement in the Boolean algebra. And we define a whole new order, not the lattice order that we had in the Boolean algebra, by taking essentially that lattice order and restricting it to these two bits that we've cut the Boolean algebra into. So we take a proper prime filter, we take its complement, and then we define this order so that it holds in one of these two cells just when the lattice order in the original structure held, but that no order facts hold between these two halves. Now, note, we're going to have for any A in our original Boolean algebra that A belongs to D if and only if not A belongs to U, given that this was required to be a proper prime filter. And so we'll know that nothing is going to be below its Boolean negation with respect to this new order or above it. And in particular, for any A and B in this new order, either A won't be below B or it won't be below not B. And so we get an SK complemented poset. Note, however, and this is why I should have omitted these two symbols, this thing is going to have neither meets and joins. In particular, because if A belongs to D and B belongs to U, there won't be anything that is below both of them at all. So there won't be a meet definable with respect to these two elements. So here is a general way of constructing an SK complemented poset. I'll briefly talk about how this works in the case of CC1, although given that we saw this semantics already, I can breeze through some of the details. We take a matrix presentation of CC1 as follows, and we can define an order in terms of whether an implication is satisfied. So whether its value belongs to one of the designated or is one of the designated values. And if we do that, we obtain an SK complemented poset of this kind. So we take this to be our proper prime filter, say, and that to be its complement. And we get something where 4 is the negation of 2 and 3 is the negation of 1. And so you can just look and see that none of the required, or none of the order facts we're meant to avoid hold. However, it's also easy to see just by looking that this is not going to be a maximal SK complemented poset because we can define a proper extension of this by either collapsing 3 and 2 down to one element or 4 and 1 down, or doing both. If we do both, then we get basically a what could be called a discretely ordered 2-element set, one of which is the negation of the other, and that's about as simple an SK complemented poset as you can get. Right. So there's one example showing that the definitions I'm proposing are in fact a generalization of at least some existing work on algebraic semantics for these kinds of functions. Another way to do it, and this is in a way even simpler, is to take a Boolean algebra and to just chop off the top and the bottom. And in fact, it's relatively straightforward to prove that if you crop a Boolean algebra like this, just chop off these things, what you'll get is a maximal SK complemented poset. To see why this works, note that if you collapse any of these pairs down, you're either going to get that something is comparable with its negation, or you'll get that something is below something else and that other else thing's negation. So for instance, if we say collapse down not C and A, then B will be below both C and not C. There you go. Now, this is very simple, but it's not a particularly exciting construction, and we can do better. And in particular, unlike the McCall case and this simple case, we can build structures that allow at least some lattice operations to come along as well. And the way I'm going to proceed here is what I'll call doppelganger and then super doppelganger structures that allow us to start from a poset and then build an SK complemented or K complemented poset out of it, which allows for, as I said, some lattice operators. So whereas the McCall algebra started from a Boolean algebra and chopped it in half, we can go the opposite way and start from a poset and double it. And then as with the McCall algebras, we chop a Boolean algebra in half and put all the negations of things in one half and the other half. Here we can take a poset, double it, and put all the negations of things in one half and the other half. And that way we can also get posets that don't satisfy the things we don't want to satisfy. So here's a way to do it for getting K complemented stuff. Fix a poset and an isomorphism with this as its image. Now, a doppelganger of our original poset is going to be a triple where we define the order so that it holds between the two halves, just in case it already held between the two halves. And it only holds from one half to another if you're going from the new half to the old half. And furthermore, the thing in the new half needs to be strictly below the image of the thing in the old half. This strict requirement is to avoid satisfying things being below their own negation. I'll show you a picture that will hopefully clarify what the definition is getting at. And then we take negation just to be the star and its inverse if we're in one side or the other. So in general, this definition puts elements in the new half below elements in the old half, and strictly below if we, for instance, consider the image of something in the image in the new half of something in the old half.
Yep.
Yes.
10 minutes.
10 minutes. Okay, great. So here's some examples. If we start with the two-element linear order and we split it, we take its doppelganger, we get two copies of that linear order where we only have one order obtaining between the two halves. And that's just because A star can't be below A, lest we have that A is comparable with its negation. We can do it with a three-element linear order, not linear order, sorry, a three-element joint semilattice. And my partner was very excited when she noted that this can be presented planarly. She was a graph theorist. And we can do it again with a four-element distributed lattice and so on. So this is the kind of picture of what we're doing. We take two copies and then we stick in interstices in a way that allows some comparison, but not the kinds of comparisons that will get us in trouble. It's easy to prove that any doppelganger of a poset will be a K-complemented poset. If you don't believe me, look again at these and then imagine we add more elements. So that's nice. And furthermore, we can use this to show that every poset embeds into a K-complemented poset because that embeds there, that embeds there, and so on. So we keep the original structure in the new one, we get this immediately. So this tells us that K-complementation is actually a pretty easy property to get. It looks like it's strict, but in fact, we can always sort of build K-complemented things in this sort of way, which I hope will provide some means for taking results about posets and pushing them across the embedding to get results about K-complemented posets. However, we can do a little better if we start from a poset that already has some nice properties. I didn't say this, but I'll say it now. If we start from finite posets, then doppelgangers don't wind up as lattices. Basically because we're not going to get meets for the tops and bottoms of the original thing, lest we then get tops and bottoms in the new thing. So if we want lattice operators, we need to go infinite. But we can. This is just to say what I said, but with the word theorem at the top. And as I said, in certain special cases, we will get lattices. And at least in one case, we'll get a distributed lattice, which makes my heart happy. So suppose we build a doppelganger on the integers with their usual numerical order. If we do that, we get a K-complemented distributed lattice. Here are two definitions that you don't need to take on board. Just note, we need to use the integers because we need to have predecessors and successors defined in order to make this work. But if we do, we can, in fact, define lattice operations and get a structure that looks like that, which I've called the Kapsner ladder because it looks like a ladder, although one where the rungs are unhelpfully angled. But if we do this, then in general, as I said before, we put stars below things that are not stars, and we keep any point at its star apart by sticking them on the sort of sides of the distributed lattice, and then we just copy that infinitely many times along the integers. So for instance, we get that any instance of a contradiction will belong in the stars, and any instance of occidental will belong in the original thing. We will satisfy both of these strict inequalities, which goes to show that in fact these properties are compatible with being K-complemented. And given the definition of negation. Negation is trivially period 2. So this one model goes to show that there is at least some stuff that's compatible with being K-complemented. But we also do get that negation is not going to be monotone. So if something is below, if A is below B, it's not the case that not A is not below not B. So negation is neither antitone, that is order inversing, nor monotone, which is funny and strange. But I think funny and strange in a hopefully interesting sort of way. Okay, so that's one relatively simple example we can give. And furthermore, this is a maximal K-complemented distributed lattice. You can't collapse down any pair of elements without introducing an inappropriate, which I won't give the proof, but look, there's a picture. Anyway. And in fact, it's easy to apply a similar kind of ladder construction to get all sorts of other things. So one that I mentioned and talk about a bit in the paper version is if you start from, say, the canonical non-distributive modular lattice and just add ladders coming off it in the right way, then you can define a K-complemented non-distributive lattice out of it. And you can do similar kind of stuff. It turns out K-complementation really likes this picture. So if you stick that picture on in the right way, then you can get K-complementation out of it, so long as you really go infinitely both in upwards and downwards. But this particular construction is intimately tied to K-complementation. And so in particular, it won't work for SK complementation because, hey, it gives rise to things that have meets sometimes. So let me talk about, I guess, and in closing, talk about how to adapt this construction to get SK complemented stuff. And that's what I will call super doppelganger structures, where, again, starting from a post set and taking a copy of it, we build a super doppelganger by fixing the order to hold, once again, between anything in the original set where the order held already. But now we require that it holds between two things in the new set, just in case they're identical. So we don't actually introduce any orders between things in our star post set. And we have orders between things in the star and things in the original as before, just in case there's a strict order between the thing in the star and the image of the star. That should be a pre-image. Anyway, we only hold the if there's a strict order, like in the old case, and we define negation as before. Then it's easy to show, again, well, there's a lot of cases, but if you go through the cases, it's more or less routine. Any super doppelganger of a post set will be an SK complemented post set. And in particular, if we start from either the naturals or the integers, then we get nice looking SK complemented joint semi-lattices. Defined this way, and once again, we need something with a discrete order so that successor is well defined. But we get pictures like that, where we've got these infinite joint semi-lattices, which either extend downwards forever or which stop in a pair of minimal elements of a thing and its negation. And both of these are maximal SK complemented joint semi-lattices. So that's a fact. There are some things you can prove about negation in these that tell you certain properties that are compatible with being SK complemented, but given time, I'll have to ask you to look at my paper rather than these slides to find out. Right, so let me say a little bit about what I want to do. SK complemented semi-lattices, one of the reasons they're interesting, both in the SK and the K complemented, is that we're not talking about varieties. We're not talking about classes that are definable in terms of equations. We're talking about what by Gorbanov and Kravchenko have been called anti-varieties. These are classes of algebras, none of which satisfy any of a collection of equations. So it's about not satisfying equations. But what do anti-varieties and the logics of anti-varieties even look like? As far as I know, there's been next to no work on anti-varieties. I know the definition has been stated, but for instance, I don't even know if we have like a Birkhoff-style theorem connecting anti-varieties and closure properties of sets of algebras. So this is the Wild West, and I think it would be interesting to know more about what anti-varieties look like to then get some results about these logics. That's one thing. Another thing is what kind of implications can we add? So I originally said one of the advantages of going Kapsner strong is we can get rid of implication and talk about negation. But we're still talking about complexive logics in some sense. So it'd be nice to be able to also talk about implication without requiring it to play this double role of both connective and Tillman relation. So what kinds of implication operators can we add to say K-complemented distributive lattices like the Kapsner ladder? In the paper version, I look at a few like material implication and a Sugihara style implication, which is used in logics like R-mingle, in case you're familiar with that, I'm curious. Both of those give rise to some really odd results. And none of the other examples I've looked at for how to define implications give rise to things that smell like implications. So there's a question of what other options are available that would give us some nice results. And in particular, allow us to, say, give algebraic characterizations in terms of K or SK complemented coalgebras of strongly connexive logics and not just Kapsner strong logics. I think that's an interesting question. Furthermore, there are tricks when you don't have bounds with getting residuation to work nicely. So one of the nicest ways to define an implication is to define a sort of groupoid style operator, a monotone binary operator, and then define the implication to be the residual of that. But this looks real strange when you don't have bounds, because it makes it very hard to define residua in a way that looks good. So how do you get around that? I don't know. Be nice to know. And related to this, I don't know, but I'd be very curious if there's some way to get representation results or lattices, posets in the area. Like, for instance, the stone representation of Boolean algebras in terms of fields of sets, or the sort of gaggle theory style representations in terms of prime filters and relations representing operations. But the fact that we're dealing with things that are anti-variety flavored seems to put a stick in the spokes of the representation theorem wheel. So I have no idea how to get around that, but I think it's very interesting and likely to give rise to some new stuff. And if we could give representation results, we could get some frame-based semantics, which I like frames. Frames are neat. We know what they look like, and we even have a sort of relatively cut and paste philosophical interpretation, unlike the kind that we have in algebraic semantics. So it'd be nice to get some representation results to then study frame semantics as well. Finally, and I already said this, but that's it. Here are some references. If you want the paper, let me know, and thanks for your attention.
Questions? Wolfgang, please.
Okay, thank you for this paper, talk. With so many impressive technical details. As a philosopher, of course, I cannot enter into any of these details, but just even maybe naive question concerning the starting point. I have to admit that I always wonder if there is a real substantial difference between Kapsner's characterization of connexivity and the usual one. The usual one derives from Aristotle's work itself. This morning, we learned that Aristotle told us any proposition, if I generalize your example, any proposition of the type that the proposition is implied by its own negation is impossible. Okay. What is the difference between the impossibility which Aristotle has in mind and the unsatisfiability which Kapsner explicitly postulates? And again, what is the difference between these semantical characterizations of a certain implication versus its syntactical property so that its negation is provable?
Yeah, so with respect to the first question, I think it is interesting if you think about impossibility in this strong sense of not having any models. So looked at in that respect, the unsat one condition may well be a better representation of the kind of impossibility claim than the true valid negated implication claim. Although I don't want to pin myself to that claim, but I think it's interesting and plausible and one that I'd like to think about more. With respect to the second point, one of the things that I like about algebraic semantics, and this is a point that's been emphasized by, for instance, Hiroakira Ono, is that you can think of algebraic semantics as a piece with syntactical methods or proof theoretic methods, so that algebras and proof systems are sort of similar in a respect. And that's sort of what I'm doing here, is looking at the syntactic form of the unsat clauses and then fixing classes of algebras precisely to characterize what those syntactic forms give us and what they don't give us. So the method here is one that takes the syntax very seriously at the possible downside of having semantics that's maybe less intuitive than, I don't know, say the done sort of relation style semantics, or as I mentioned on the previous slide, the frame-based semantics. So I think of this project as being very closely tied up with syntactical considerations. And one of the things I'd like to do going forward, as I mentioned, is to think about the upshots for semantics, but as of yet, the technical hurdles in trying to make that precise are, I don't know, maybe they're not all that substantial, but I haven't managed to clear them yet. So I'd like to have a deeper answer to your second question, but I'm afraid I don't. That's as far as I can see tied up with the way I want the project to continue.
More questions? There's a Aileen in the so please. Andy, sorry. Hello.
Thank you very much. Of course, I'm very flattered by the terminology and in fact, I've seen an earlier draft of your paper, and when I told my folks that someone named a ladder after me, they didn't believe me. But I said, no, it's an abstract ladder. You can't use it for anything. And they said, oh,
and the rocks are all bent. I mean,
yeah, and if you tried to use it, if it was concrete, you would break both legs using it. And then they said, okay, maybe that makes sense. That is named after you. Well, just a little observation and then a question. I'm just really finding it interesting that even though in the earlier paper I was writing about implications and so on, I'm myself moving much more towards thinking about conditionals in these kind of matters, and seeing you taking that same first step in completely the other direction where it's really not about conditionals at all is really, really fascinating. I was just wondering about the anti-varieties, about the literature on that. You said there isn't much, but was there some point they had in introducing the idea? Is there some concrete examples they're discussing that are understandable, easily explainable?
No. So as far as I know, there have been 3 publications that have discussed anti-varieties. One was a Russian textbook written in the 60s. One was a monograph also in, well, I don't know if it was in Russian, but written in Russia by Russians. These are Kravchenko and Gorbanov, who I mentioned. And then a paper by the 2 of them talking about certain graph theoretic properties. And basically in none of those do they give like simple concrete examples. Rather, it seems to me like they gave the definition sort of out of a desire to be complete. So there are papers talking and books talking about varieties and quasi-varieties. And so they thought, well, we're talking about equations and, implications between equations. What about negated equations? If we talk about, say, universal Horn clauses, for instance, we can talk about negations. And so I think they introduced the terminology and the concept just to fill a sort of technical gap. Like, if we're talking about classes of algebra that are like this, why not talk about classes of algebra like that? But they don't give any sort of simple, graspable examples. And one of the things I'm very happy about with this project is that it seems like there are at least reasonably well-motivated examples of anti-varieties, which it seems to me are the kinds of things you want in order to motivate people to think about anti-varieties. So one of the things I'm hoping that falls out of this is that I can convince some actual algebraist somewhere to study anti-varieties by saying, hey, look at my posets, look at my co-algebras. Ain't they pretty? Don't you want to know what they're like? But no.
Full generality.
Say again, sir?
In full generality, would you like to know about?
Yeah, exactly.
Very general picture.
Yeah.
Thank you very much.
Thank you.
Yeah, great talk, Andrew. I have two questions, simple ones. So you said you still talk about connective logic in some sense. And this, of course, would bring me to the question concerning implication.
Yeah.
And you mentioned the problem with residuation in the previous slide.
Yes.
But what would you then consider as a genuine implication? This is the first question. And the second question, in view of the previous talk, you're studying from partially over the algebras. Would it make sense to give up reflexivity or transitivity?
Oh, so
we have Q and P consequences.
Yep. So with respect to the first question, I don't know if I have a well-developed view on what are the essential properties of implication. The views I have with respect to is this operator an implication or something else tend to fall into like family resemblance kind of views. So one way to look implication-y is to residuate a monotone binary operator. Another one is to sort of kind of look like material implication. But I'm happy to avoid trying to adjudicate the question of whether these things are really implications or not, and instead look at the question: how many properties of other operators that we're happy to call implication do these satisfy? And so, to what extent do they smell like implications? That's at least the methodology I've been taking so far. And the issue with residuation just comes from the fact that in lattices, oftentimes if we have a monotone binary operator, we can define residuals using generalized joins, or go from implications to define monotone binary operators that they residuate using generalized meets. But if you don't have tops and bottoms, then you're not in a complete lattice, and so generalized meets and joins don't generally exist. That's the issue. It might well be that in certain specialized contexts we can get around this if we don't require too much residuation, but it's a little bit. This is something I've discussed with Francesco Paoli, and it's related to some work he's done on like half residuated operators that we might be able to get away with in certain contexts. That's one of the things I want to think about but haven't gotten around to yet. So that's what I can say in response to the first question. In response to, or also there's the kind about connexivity in some sense. The point that I was making was we're in logics that are in the vicinity of connexive logics in the sense that if you think about connexive logics, these are some other logics we might want to think about. I have to admit, in answering the previous question, I forgot what the second question was. So can you remind me?
You're giving up reflexivity.
Sure. Yeah, I mean, so reflexivity doesn't seem like it should be a big problem, because then what we're thinking about are strictly ordered algebras rather than loosely ordered algebras. Transitivity is trickier. I mean, if you give up transitivity, it's not clear in what sense you're talking about an order at all. Which might be an interesting thing to look into, but I don't have anything to say about it now. One thing I will say is that the strict order, as you saw in the doppelganger constructions, is used a lot for this sort of these kind of constructions. And so it might well be that logics of strictly ordered K complemented and SK complemented things behave in some nice way, even if they're not reflexive. But that's not something I've thought about.
There's another question that comes to my mind, but
it's okay because there's another question, and I think that we have just time for one last question.
Well, I don't know. I have lots of opportunity to discuss. So that's I can just go down the hall.
One comment, one question. The comment is for a long time, some years, I was happy with Falls' definition of connexive logic. I was used to refer that definition even when I was preparing papers. Define connectivity in this way or other ways I would reject it. But nowadays, I would say that connectivity is more like relevance or constructivity. Also, that are not really precise, but rather are a family of related principles. And I have that feel of connectivity. And I like this work because it stresses the role of negation in isolation from negation. I think that's nice, but also stresses the importance in this context of the order negation, which is new to me at least. And thinking in the logical side, it would highlight the importance of the consequences relation. And thinking of connectivity at the level of consequence relation is there are some ideas here and there, but I don't think it's systematic study. Connectivity at the level of consequence. For example, like Abraham's work on relevance at the level of consequence. I like this approach very much. The question is about the oddities of combining the serial implication of this arrow is lattices. What kind of oddities?
Well, you get things like that material implication doesn't have the kinds of tonicity properties you would usually ask for, like that it's monotone in the consequent place and antitone in the antecedent place. I'm happy to send you the paper that goes through some of these examples of things where material implication goes wrong. I have to admit I don't recall more than that off the top of my head, but what I recall is thinking, oh, material implication is really ugly in this setting. Even uglier than yeah, it's just that negation behaves strangely enough that combining it with disjunction doesn't give you the kinds of property you'd expect. So you do get things like, for instance, that any formula entails any implication. A always entails B implies A. So you get sort of weakening kind of principles like that, just in virtue of how joining behaves. But a lot of other structural properties of implication fail. Although I'd have to look at the paper again to remember. Things look weird. With respect to your comment, I'm also more than happy to think about connectivity as a determinable kind of thing. Although I don't know if anything hinges on that, but I'm in agreement with you more or less that issue. Thank you.
So I'm afraid we are very much time. So thanks. See you tomorrow at 10, right? 10.